Cloud. All right, we are gonna start with our workshop today. So welcome everyone. So today's workshop is mostly gonna be based on teaching you guys the intro to Keras and building neural networks with them or models, and also kicking off our neural network modeling competition to let you guys show off all your skills you've learned through our past workshops, or if you haven't been to a network workshop, just flex your skills and get on top of the leaderboard. So here's a quick outline. I'm gonna guide you. So this is like a live coding workshop. We're gonna ask you guys to all code with us if you like, and we'll try to help you guys as much as possible to get set up with the environment, and show you different ways to start writing code. So the first thing off is what is I should present this. Oops. What is TensorFlow/Keras? So TensorFlow is an API in which it makes it much easier to create neural network models and deploy them as compared to using standard data processing Python libraries. So think about using NumPy to do giant matrix multiplications and then iterate over and over and make an entire framework out of that. So Keras is an API designed for human beings, not machines. And why? So with deep neural nets, the decision on what architecture and hyperparameters to use is much more important than what language or library is being used to implement the model. So TensorFlow/Keras ends up saving a lot of time, especially for researchers, in the implementation of the neural network, as the code becomes very straightforward and much more easily readable. All right. First thing, guys, make sure to install TensorFlow and Keras and Pandas. You're gonna need Pandas to load the data, although you can use other methods, but we recommend Pandas. So these are the commands. This is one way. If you don't want to install this on your computer with pip, and prefer using Anaconda, actually, I don't think anyone here is going to use Anaconda. If you want to use Anaconda, let me know. I can show you guys that as well. Otherwise, I assume most of you guys have Python installed. Make sure you have Python 3 and pip 3. All right, Bernard is all set. Just make sure you have TensorFlow on that Anaconda distribution. If any of you guys have any problems, text in the chat or open your mic and let us know as soon as possible, because we want to make sure everyone's on the same page. And also, this takes a bit of time to install, actually. Or text Catherine. Is she even in this chat? Okay. Let's move. And I'm gonna, if you guys don't want to install this locally, I'll give you guys a second option. So second option is using Google Colab, which I highly recommend. This is helpful if your computer isn't that powerful. And it also gives you an option to use like GPU runtime, which I'll show you how to use. It has tons of packages available, including basically every single machine learning library you ever need. Caveat, it's not actually collaborative. They actually turned off the real-time collaboration feature on Google Colab a while back, mostly because it's very hard to make people collaborate on a same notebook with the same kernel. So if you want, make sure, go to this link and I'll go quickly demonstrate how this works and how to get set up. So what you want to do is go to Google Colab, colab.research.google.com. It'll give you like the starter page. What you want to do is you want to click File, click New Notebook. This will then open an empty notebook for you. And you can give it a name. And I'll quickly show you guys what to do, because the first thing you want to do is you want to decide on your runtime. So if you go here, you click, sorry, I'm going to show that again. If you click runtime at the top, click change runtime type, you can change this from GPU to TPU. I don't recommend using TPU because I think it actually costs money. GPU is actually free. So you can actually use it, you can click save, and it'll reset your runtime to GPU. Important note, when you switch runtimes, it will delete all your temporary data. So all your output, your cell output, and local variables will all be deleted. If you change your GPU runtime, that means you have a GPU available to use. Well, you still use a CPU actually, but you have the option to use a GPU. And I think TensorFlow will, by default, use a GPU if possible. Another thing to note is don't use a GPU if you don't have to. Like if you're just doing a simple analysis or building simple models, don't use a GPU because it's gonna cost you money. And at one point, Google is just gonna stop your runtime and just stop you from running. So I'm gonna actually not use a GPU because I don't need it. And now we're gonna go through setup. So I'm gonna be coding on Google Colab, and it's basically the same way as you code locally. So if I show my VS Code here, where's my VS Code? This is very slow. Here, I'll just open a random file. Let's look at, I'm just gonna use Google Colab the same way. Look at a comment, yeah. All right, first thing, I'm just gonna give a quick neural network refresher. This is like the fastest refresher possible. This doesn't cover anything, but this is the minimal, I think, amount of information you need to start building a network and try to like guess what you can do. So a neural network is composed of stacked layers, typically, that transfer input into some output. So you can see on the picture on the right, you have these 4 layers, input layers, 2 hidden layers, and 1 output layer. So what it does is it uses training data and a loss function, and our neural network learns to approximate the closest function that minimizes that loss. And when it's learning, what's effectively doing is updating each of those lines, which represent weights, which are parameters of our network. Think of them as parameters of some function, like a quadratic function. Parameters would be A, B, and C, right? The input layer takes as input a raw input, takes in raw input to feed to hidden layers. So if your input layer is of size, if you have 5 neurons in your input layer, that means your input shape is 5, 1, meaning a column vector of 5 values. Output layer then takes the output of the hidden layers and transfers them into reasonable outputs for loss function to use. All right, any questions? Cool. Here's the setup. I'll copy these 4 lines. These are the first 4 lines you will always want to include. So what we're doing here is we're importing NumPy. This will help us just load some data. Second thing is you want to import TensorFlow as TF. TF is the most common acronym for TensorFlow. Then to start using Keras, I recommend importing the following. So from TensorFlow, import the Keras module, and then from TensorFlow.keras, import the 3 modules, models, layers, and losses. And I'll show this real quick live on Google Colab. So here's what we're gonna do. Import NumPy as MP, import TensorFlow as TF, import TensorFlow, from TensorFlow, import Keras, from TensorFlow.keras, import models, layers, So what you're gonna do is you can press this play button. You can also press Shift Enter and it'll run the cell and it'll start loading your data. Let me know if anyone has had any issues with this or anything. All right, next slide, data. We're gonna need NumPy arrays. We have many methods to specify the data input to our neural network. So we can either use NumPy arrays, TensorFlow tensors, TF datasets. These are very complicated and I won't explain them, but I've left the link in there. And Python generators. So the way it works, NumPy arrays just work the same way you think it works. The NumPy arrays must be, you have to have 2 NumPy arrays, one to specify the input and one to specify output. I'll show an example later. You're also going to need TensorFlow tensors as another option, which is basically NumPy arrays, but TensorFlow's NumPy arrays. They're not really that much different. The only caveat is that TensorFlow tensors can be located on your CPU or your GPU. As for why that happens, don't worry about it. It's just that sometimes memory for GPU is separate from your CPU. So what TensorFlow does to optimize is it stores variables on the GPU or the CPU. But you guys don't need to worry about it. We're not going to cover tensors at all because you just don't need to know about it. TF datasets, I highly recommend learning about, but this is a more advanced topic. The point of TF data is to parallelize and improve data pipelines. So let's say you're pipelining a video into your, let's say you're pipelining video frames into a model. That takes a long time because you have to, every iteration you're reading images from your local disk. So instead, TF data will help cache data in your memory, parallelize the task, and help train faster. Edward, can you help Anish real quick? All right. The last method is Python generators. So what I'll show an example of this, but I don't recommend using this because this is a bit more advanced. The point of Python generators is to yield tuples, inputs, targets. So inputs is your input data, targets your labels, or an array of those tuples for learning with batches. And I'll explain what batching is about later. Here's an example. So here I was working with a video data, and where is my, here we go. Here's an example of a Python generator. This looks very complicated, but this is all it's doing is running an infinite loop, and then it's gonna generate or yield an array of images, a batch of images, and a batch of speeds. This thing is estimating speed data from videos. So all this is really doing is shuffling the data taking the next 32 images, reading them from the disk, and then giving TensorFlow the data. This is a very advanced thing. You don't really need to worry about generators. I actually think you rather want to use data sets instead, TF data sets. So let's just generate some arbitrary data. Let's see. Wait, why is this not working? A range. Let's just say x equals this. Y is equals np.a range to the 2000. All right, so I just generated some arbitrary data, x values and y values. The function we're gonna learn is basically mapping from 1 to 100 to 2 to the 2000. So it's pretty easy to map. Oh, actually, I should make this the same steps. This is not right. Let's do 10. And I'll print out the shapes just to double check they're about the same size. Nope, I can't count. All right, so let's just pretend this is our data. Wait, what? Okay, I really can't count. So now we're gonna start the fun part. Let's try building our model now. So the first API I'm gonna introduce is the sequential model. This is a really common model, and this is the one provided in our starter code. If you don't have the link already, there is starter code for our competition already at this link here. Post it in here. So if you check the starter code, Edward kindly provided us some code to load your data here. Don't worry about this section of code. This is just loading your data. He provided a sample usage of using a sequential model, and I'll explain what each of these things do. And also this code, as a starter code, also saves your results to a CSV file for you. So all you need to worry about is making a good model here. Anyway, less about that. Let's start building our model. So the first thing you want to do is you want to initialize our model. So we do model equals models.sequential. So this will initialize an empty model. The next thing you want to do is you want to add a layer. So what we're going to do, oh, this doesn't work yet, but what you want to do is you're going to add a layer object. So I'm going to talk about the layer object in a minute. But let's just say we had some hypothetical layer object. What this will do is it'll tell Keras to pass input from the current last layer of the model onto the new layer. So I'll give an example. If we did this, this is equivalent to doing this kind of neural network. It would be layer 1, passing input to layer 2, passing input to layer 3, passing input to layer 4. And here, our input, let's make this a comment. Input layer, this is our input layer, hidden. This is hidden, and this is our output. This is an example. Here's a second API you can use. So this is called the functional API. This is more advanced. It's a little bit slightly more complicated, but if you're used to functional programming, this would make a lot of sense. The difference between functional and the sequential API is the sequential API forces you to build a fully stack of stack layers, but whereas the functional API allows you to do more creative shapes, such as the architectural model used in ResNet, where it had like a pyramid kind of thing going on. So I'll show an example of building a model using the functional layers. So I'm not going to run this code because that won't work actually. What we first start off with, we start off with an inputs function or inputs layer. What we're going to do is keras.input, and we're going to specify the input shape. So we call our input data is just linear data, one-dimensional. So we're going to say our shape is equal to 1 comma, which means it's linear, one-dimensional. We're going to run that. Next thing is we want to start creating our layers. So I still haven't gotten to building layers yet, but similar idea. We functionally apply layer objects onto the previous layer's output. So what we're going to do is, for example, the above code here is basically equivalent to this. X equals layer 1. Let me call this layer 1. Layer 1 applied onto the inputs, and then we forward pass our output to the next layer. So you see how this is functional. We're kind of applying functions onto functions up to inputs. And then we do layer 3, and then we do layer 4. And actually, layer 4 is actually our output. So actually, I'm going to call this outputs instead. Outputs with layer 4 of X. And then the final step for the functional API is to now complete the model by defining the model. So we do model functional equals keras.model inputs equals inputs. It's not recognizing it. Inputs equals inputs, and outputs equals outputs. Slow down a bit. Yeah. Ishan, do you need any explanations about the functional API? Here, let me just quickly reiterate what this is doing. So what we're doing is we're simulating passing data in. So we're going to say the input layer is this, is taking inputs of shape 1 comma, which is correct because our data here is linear. A range just gives you a linear set of data, of one-dimensional data. So we have one-dimensional data that we're feeding into the Keras. And what we're first going to do is we're going to use the first layer of our neural network and pass the inputs into it. So layer 1 called onto the inputs produces output X. And then we're going to continue applying the next layer because that's how a neural network works, is stacked. We apply the next layer, layer 2 onto X, which is the output of layer 1. And then we reset X to equal the output of layer 2. Then we set X to equal the output of layer 3 applied onto the output of layer 2. And then we create outputs, which is the output of layer 4 on the output of layer 3. So again, this creates the same design here. We have an input layer, hidden output. All right. Any questions about either API? Both APIs do pretty similar things. And for the scope of this competition, both will pretty much give you the same performance. It's just that the functional API lets you do more funny things. All right, cool. Now here's the fun part, creating the layers. So recall that before, all of these layers are called layer 1, layer 2, layer 3, layer 4, but they didn't actually do anything. So now we're gonna actually call define layers. So I'll give an example. Typically what we'll do is there's many layers available: dense, convolutional, LSTM, dropout, and so forth. Today, I'm just gonna show mostly about the dense layer because that's pretty much the only layer you need for this competition. You can try the other layers, but okay, dropout actually might be helpful. But column 2D and LTM don't make sense for a competition, and you'll see why later. You can go to this link for full documentation details. But let's just go through developing our model. So what we're going to do is we're going to define our layers. Layer 1 equals layers dot dense. Where's autocomplete? Okay, dense. And we're going to specify 10, meaning the number of neurons. And don't worry, I'll explain the full hyperparameters of the dense layer later. Like there's a ton of things you can see here. I'll explain all of them later. And we're just going to say activation equals linear, which is actually a bad idea, but let's just do that. And let's just do the same thing for other ones. Layer 2, layer 2, layer 3, and layer 4. Other thing to note is remember of our output layer needs to output the same shape as the labels, which is one-dimensional. So we're actually going to make this 1 neuron. So let's define this. Create our layers. We're going to add these layers. And here's a nice function you can use. You can use something called model.summary. And this will give you a text-based output of what your model looks like. JK has not been built. I am maybe missing something. I think I need to compile first. Oh, sorry, I need to compile something first. You need to do this first. Yeah. So after you create the layers, as I've done here, I just added all the layers. What you want to do now is you want to compile it. So let's compile this using one of these optimizers. I'm just going to copy the code from the starter code. Let's take this. Let's use Atom, and let's use mean squared error. Compile. Okay, now this should work. If this doesn't work, I'm just going to skip it.
Wait, start.
Oh, I forgot the input shape. My bad. What was okay, this is another caveat of the sequential API. You'll notice that in our functional API, we specify the input shape, which is required for any API, like this, shape equals 1 comma. When you're doing the sequential API, you have to make sure your first layer has the correct shape. So this is actually 1 neuron, which is an input layer. And what we do is we do input underscore shape equals 1 comma. My bad, I made a mistake here. Let's reset our model, create our layers again, add our layers. And now this should work. There you go. So if you run the function model.summary, This will give you a nice summary of what your model looks like. So this is, we have dense layer taking input, outputting one. Oh, we don't actually need, okay, whatever. Let me fix this again. I made a slight mistake. Once again. So remember, our first layer takes an input of 1 dimension, expands it to 10 dimensions. Next layer takes in a 10-dimensional input from the output from previous layer, produces a 10-dimensional output, so forth, so forth. And our final layer produces a 1-dimensional output. You'll also notice this will tell you the number of parameters you can train, number of trainable parameters, because some parameters you can't train actually, depending on your design, and the number of parameters used for each layer. Any questions about this so far? All right. Next step is compiling. So once we have our model object, we want to use model.compile to tell Keras what to use to train our network with. So what we need to do is we need to pass in an optimizer, a loss function, as well as metrics to track. So you see an example here. The first bit of code asks the model to compile using RMS prop as an optimizer, using a learning rate of 1 to the negative 3, or and uses categorical cross entropy as loss. All these loss functions and optimizers are stored in Keras.optimizers or Keras.losses. Model.compile, the second one is just using atom optimizer. Uses mean squared error as a loss, which is the one you'll be using for this competition. And in metrics, it wants to store an output during training is mean squared error as well. So let's take an example. We're going to go ahead and compile our model. Works fine, no errors. And now we're going to do the fun part, training. Oh yeah, Daniel, sorry. I made a mistake earlier. You need to pass in this. So do you see this part here? You need to give it input shape equals 1 comma. Did you rerun it? You should do rerun. Make sure to rerun model equals models as sequential. Rerun this and rerun this. You might be having like if you didn't reset model, it might cause an error because it thinks your first layer is still the old one. Make sure to reset your model variable. Where can I find a link to the competition? So this is a competition website. Let me go quickly find this. Okay. You're not using Colab. Can you show Edward the script, or Daniel, can you paste the script into the channel somewhere in the Discord? And Edward can help you out real quick. All right, next step, training the model. So using the compiled model object, you use the function model.fit, and it'll basically fit your model to the data. It'll basically learn it to approximate the function that maps from your inputs to your outputs. And what it also does, it returns a history object, which has details in loss and other metrics about and other metrics such as mean squared error over the epoch number. This is very helpful, and this is also in our starter code. So when you're training the model, what we want to pass in is the inputs, desired outputs / labels, along with parameters such as epoch, batch size, which I'll explain later. If you're using tensors or NumPy arrays, you only need to specify x equal and y equal keyword arguments, as shown in the first example. Model.fit, x equals x data, y equals y data, which is what we're doing here. You can also specify a validation data set in 2 ways. You can do validation split equals some percent, like 0.2, or you can provide your own custom validation data. So let's look at this. We're going to train this on our fake data we made earlier. Model.fit, x equals x's. Did I call it x's? Yes, I call it x's. Y equals y's. Epochs, let's do 10, and let's just do this for now. And this should start running. Okay, that was very fast. It did not learn at all. Let me see what happened just now. Error. Oh, I mean, it's kind of obvious why it doesn't learn. We have a very bad model. And also, we should probably change the learning rate. But yeah, you'll see this loss. Let's do, and I'll show an example of using validation split. Let's do validation split too, and let me just add more data. Documentation. Let's do from 1 to 1,000, 990. Just create more data for it to train on. We're gonna reset our model again. So we're gonna recreate a model to reset the variables. Again, a summary, same thing. Compile our model, and then let's just train it for like 100 epochs. So you see a nice thing here is now it shows validation loss as well, in addition to mean squared error, other loss functions. So you see this trains pretty nicely. Goes from, I think, 1.6 million, 16 million, all the way down to about a mean squared error of 34, which is pretty good. Oh, okay. I think my recording might not be that great, but yeah. I just go through a bunch of data metrics. You don't need to worry about this. I just showed an example of model.fit. So does everyone understand what model.fit does and how it works? This is the key code. You pass in the X values, you pass in the Y values, specify a number of epochs, which I'll explain what it means later. You can also specify a validation split, which I highly recommend in order to help you hypertrain your model. Yeah, thank you for stopping me, Bernard. I know I'll probably go too fast all the time, but yeah. So using this data, this output, you can then decide how to optimize your model. And I'll talk a little bit later about hyperparameters. So you see, for example, validation loss is very high, not that good. You probably want a very low mean squared error, given the fact that our data is actually very linear. Like actually I'll visualize. We don't need to visualize this data. It's fine. It's very bad data modeling. And like, I mean, we have a linear network. It's very hard to learn. All right, next step, predictions. This is the next fun step. You get to see how well your model is doing. So what we're gonna use the model.predict function. Is it y equals 10x? Yeah, it might be. And what we do with model predictions is we pass in data to predict on. So it could be your test data set, which is what you would do for competition. Or you can use your training data if you just want to see how it does on training, which really is not a good idea, but we're just gonna do that for our cases. So we pass in data to NumPy array of the same shape as an input shape specified in your model, or a generator or a TF data set that yields the same shapes. You can set verbose equal to 1, this parameter, just so you can see the progress. So we're going to take a look and look at the predictions. This should work. Let's see what this says. I might need to specify steps. Oh, we're good. All right, it finished predictions in less than a millisecond. Great. So we can now look at our predictions. So I'm actually going to import a plotting library. We're not teaching plotting this workshop. Is it? Oh, no, it's import as good, yeah. But we provide you some starter code to help plot some things. So let's just quickly plot our predictions. And how do we do? Oh, pretty good. This is like the right data. And if we plot the actual values, we're pretty close. We are very close. Yeah. I'm actually confused why this gave me a loss or mean squared error 34. I guess the error is too hard to see here. Other than that, we trained pretty well. Yeah. And here's another note. If you do intend to use batch size, you may, and this only applies if you're using the generator or TF datasets, because Keras doesn't actually know how much data is in a generator. What you can do is you pass in generator TF dataset, you specify the number of steps to take. And this number of steps is always equal to the length of the data divided by batch size plus 1. But again, you don't need to worry about this too much. Can you show model.fit line, predict line? This is a model.fit line and predict line. I got it perfectly. Oh wait, what do you mean by model.fit line? Oh, okay, yeah. So here's the, can I decrease, I can just close, okay. So here's the model.fit line. You pass in your X data, you pass in your Y data, you can specify the number of epochs, which is the number of iterations to train on. I'll explain what the epochs means later. And you can also specify validation split, which is the percentage of your data used for validation and percentage of your data used for training. When you're doing predictions, it's really easy. Pass in your input data again. In the case of a competition, you want to pass in the test data, and then you can just store predictions. Again, this code is actually up live. The code for the competition is actually here. So you see example in our code, we do history equals model.fit. We put in the inputs, give it the outputs, pass in epoch 5. This will fit our model. After we fit our model, then we predict the results and store them into CSV. So if you have any questions, again, just check the starter code. It'll have examples using the sequential API. Any other questions? And feel free to make me go back to any slides. I'll happily go back. All right, here's a long list of things you can do. The architecture, so here's a non-exhaustive list of hyperparameters. Hyperparameters are basically things that you tune manually and things that the network doesn't learn by itself. So the architecture model is defined by how many layers there are, how are they connected, what kinds of layers, etc. There's also parameters for each layer, e.g. the number of neurons in each dense layer, the kernel size of the convolution layer, percentage for a drop, what's it called? A drop layer. Epochs, batch size, steps per epoch, parameters of callbacks like early stopping, model checkpointing, learning rate adjustments, validation, train splitting, shuffling, scaled log transforms if you want to use that, weight initialization, weight methods, loss function optimizer, optimizer parameters. There's a ton to play around with. All right, first thing, hyperparameters of dense layers. So I'm going to talk a little bit just about dense layers because this is the one you're going to use a lot, and this is basically all the things you can do. Units, the first parameter of dense is basically the number of neurons. So if we go back to this picture, that's basically this. So number of neurons here is the number of output neurons, or a number of, it's the output shape as well. So you'll see here, this has 1, 2, 3, 4, 5, 6, 7 neurons. This output layer has 4 neurons. That should be pretty self-explanatory. Next thing, oops, wrong slide. Next thing, you can specify the activation. So in our example, we specified an activation of linear, which if you think about it, probably won't work for our competition, but you can try using it. You can specify ReLU, linear, etc. Make sure to check the documentation. There's other things like ELU, leaky ReLU, TANH, sigmoid. Here's the next thing, use bias. I highly recommend leaving this true because you probably want to use this. This is basically for the bias term in weights and weighted inputs. So remember when you're passing inputs, the activation from one layer to the next layer, you're weighting the activations and you're adding biases to it, like WX plus B. So this is telling the network whether or not to use a B parameter or not. Oops. Kernel / bias initializer. So this tells Keras how to initialize the weights. The default method is global uniform. You will almost definitely not need to change these two values, but you can try. There's different other initialization methods, such as HD normal or something. And then here's another thing that you might actually want to try using is a regularization. So if you recall, regularizers for a network basically penalize large weights and help your network not overfit. So you can choose between L1 and L2, and there's actually a whole list of other things, but I recommend just sticking with L1 and L2 regularization. Last thing, there's kernel and bias constraint. This tells Keras to force the weights and bias to be within some range to keep the norm in some range so your weights aren't big. Not penalized by regularizer, but constrained by the code. Usually you don't need this. I say the only things you really need is activation, units, and maybe regularization. Any questions about the dense layer? All right, cool. Here are other common hyperparameters. I'm going to start explaining. So batch size, this is very important. This is the number of data samples to train on together before updating the model. So if you see this, you'll see that our batch size here is, I don't actually know what our batch size is. It is 25. Sorry, not 25, my bad. We have 20 steps per epoch, and we have like, I think 1,000 data points. So we do that. Our batch size here is about 40/32. If you specify a different batch size, it'll change the number of iteration steps in an epoch, basically the number of update steps. So let's say we did a batch size of 100. You should expect each epoch to have 8 out of 8. I guess we have less data or something. So yeah, you'll see there's less iterations per epoch, which means we're updating our weights less often. If you do a batch size of 1, this is online learning. Basically, you're training on every individual sample and updating. I have Fortnite. Wait, since when? Oh, I have this, but I don't use it. I play FM on it, Football Manager. Okay, epochs, this is the next thing. This is the number of times to run a full training iteration. So usually a full training iteration means iterating through all your data once and updating your model. If you set steps per epoch, which is another parameter here, which I don't recommend changing really, but you can. This tells the model how many times to update the model each epoch before moving on. So if we set steps per epoch to 20, we'll see that each iteration has 20 steps now. That means updating 20 times. Next thing, validation split. This is self-explanatory, tells you how much data, tells Keras how much data set aside for validation, BS for training. This is good because you want to report the validation loss in order to help you tune other hybrid parameters without bias. Learning rate. This is pretty common. This is for the optimizer. So for example, we specify the learning rate in this code here using this learning rate. This specifies how fast your model trains basically. And usually I recommend testing different magnitudes of 10, starting from 0.1 and just going down magnitudes of 10. If you ever see your training model for some reason producing NAN values, not a number, that means your learning rate is probably too large. So you want to decrease it. Any other questions before we start introducing the competition finally? Okay. Any other questions that are after the this Zoom meeting? Sorry, this workshop. Feel free to ask me in our Discord. I highly encourage you guys to ask them in our competition Discord. That's where we're going to be posting all our competition updates. So ask your questions there, or you can ask them in the general AI Discord. And we'll try to get back to you and help you with the competition. All right, Edward, take it away.
Okay. Can you for now help Pratik? I'm not completely sure what the issue is. I tried having him install the wheel instead of just using TensorFlow, but they should be doing the same thing. So can you help him still? Okay. Wait, do you want me to share screen for this part?
Oh yeah, can you start screen now?
Okay.
Yeah, I stopped sharing.
Okay. So as Stone mentioned before, this is where the competition GitHub is, and this is where all like the starter kind of code or like your starter pack is stored. In the starter pack, you have a starter code where there's like a simple neural network model to train on, and you can just like start off by using this as your baseline, and just like experimenting and trying to get a model that just like does better. And then you also have a function that can read data from a CSV file and also visualize it in like a matplotlib file. And there's also a function to output results to a CSV file because for submissions, you would need to submit a CSV file. There's also a train.csv and test.csv. And in train.csv, there's 1,500 training data points where we give you the XYZ coordinates. However, in test data, we only give you the X and Y coordinates. And the objective is to just get the Z coordinate, which is also the output. Yeah, so the output, so you can essentially just use the starter code to do the whole thing. Because this is a function that outputs the results to a CSV file. And you just need to output the CSV file as your results. And then it'll just evaluate it. So this is like just kind of like a demo of, or just an explanation of what the lines do in the starter code. This part just like visualizes the data that we give you. So this is like the function itself, or at least these are the points that we give you. This is like a 3D plot, so you can actually like rotate it, just like look at the different parts of it. And you can see like this kind of function's like not that really a really trivial function to figure out. So, I mean, it'll be pretty cool if you can figure out what the function this represents. And this is why neural networks are really important, because then you can try to like actually model this model out. Yeah. And then this is like the simple model that we provided in our starter code. And this has only a dense layer activated with the linear, and the second one doesn't actually have a activation function. So just any output that's outputted from this first dense layer gets directly outputted into the second one. And as Stone mentioned before, we're using the optimizer Atom with MSE Air. And so with this history equals model.fit thing, this actually runs the whole thing. It just trains the model. Yeah. And for this purposes, I just trained it using 5 epochs, but you can change it to however many epochs you want. Yeah, because generally when you train for longer, it's probably going to be slightly better. Yeah. And then this 10 neurons, 1 neuron. So for testing purposes, this is what you'll do. This part just reads the CSV file called test.csv, and then it gets the X and Y values. And using these X and Y values, it just calls predict on it, where it tries to predict what the expected point should be for each of these values. And then this is also saved into a CSV file. I use NumPy save text, but technically you probably should be using Pandas save, but it's fine. NumPy does the same thing. And so what's in the test.results CSV file will just be 1,000 different kind of like outputs, which should be the predicted Z outputs for the inputs. And so these are like some of the tips that we kind of came up with just to kind of help you. So as you can see in this graph, the part that's going to probably be the hardest to model is actually this part, because the actual function has like a really bad, really hard to understand, like this part. Like I don't even know how to explain what this part is doing. So yeah, this part is probably going to be the hardest for you to model, but like this like really smooth curve and also this flat part, this is probably going to be a little bit easier to model. So if push comes to shove, for the final results, you could essentially just train your model only on this part and just get like a really good result for this part, and then just like leave this part as, I wouldn't say blank, but just not use it as much. And so the other thing is that since we can submit files multiple times and we get like kind of like an error from submitting it multiple times, we can essentially kind of use the test data, I guess, as a secondary set of data that you can train on. Although you don't know which exact points that we decided to pick from your overall to use as your score, you can still technically just use it to see how well your function should be doing. And then also, since we're given 1.5K training data points, is there like any way that we can modify the data in which we could determine overfitting or underfitting? So that's like a question that you guys can figure out how to address. And so this is like a how to submit step by step. So the first thing you want to do, is there any problem if I install 3.8 while also having? Wait, what?
Wait. Oh, no, he meant to DM me that. Don't worry, I'll have it.
Okay, so this is a step by step. So first you go to ai.acm.ucst.com, which is this website. And as you can see, these are like the test ones, admin and stone. And then the next step would just be to log in. I don't know. Yeah, so just like log in. So then you can actually submit stuff. This is username.t2000. It's not an actual account. But then you just log into it. And then after that, you go to the competition website itself, which is you go here and then click that. And then you can just upload predictions here. Yeah, it says you need to log in. So just like log in. And then.
Wait, do you want me to show this part? Because I actually have logged in already.
Okay.
Wait, I have to share screen again. Wait.
Oh.
Is there anything else at the end? Okay, wait. I'll just share my screen. You can present the rest.
Okay.
Wait, can you stop sharing for a second?
Yeah.
All right. I'm just gonna quickly show. So this is a website. You can also show different things, but wait, what the fuck? Wait. Who has 21 already? What the fuck? Okay.
Well, this is funny.
So someone has already achieved an MSE of 21.9, which I feel like can go down a lot lower.
Mm-hmm.
But that's a good start. You're currently winning. I think this is a barcode. But basically you can click, so I'll just log out real quick. So I log in, I have my password in, click competitions, take me there, click upload predictions. Here's a random set of predictions from that output. I'm gonna click submit. Wait. Oh my God, this is an old one. Give me a second, guys. I need to add a value to the results on CSV. All right, this is pretty easy. So you need 1,000 values in there, otherwise it won't work. Let's see. So I got a score of 12.91. Oh, pretty good. I don't know how that happened, but it looks like my score so far is 12.91, which is pretty good. I don't know how that's possible. I just added a 0. Maybe, wait, did I submit the wrong thing? Oh, wait, I might have submitted the answers. Okay.
Wait, but if you submitted the answers, why is the score still really bad?
No, because I added a random value at the end, so maybe that made it really bad.
But it shouldn't impact it that much.
Wait, how did I get 12.91?
It might just honestly be that the points that we randomly selected are really optimal points.
I don't know. But just notice that these scores here are based on 20% of the testing data. So what we do is we pick like 20% of data points, and then we value your mean squared error score in there, and we show that. You can also see a score history over time. So it looks like I somehow improved from 63 down to like 20 less. And then at the end of the competition, we'll show the leaderboard with using the full 100% of the data. Anyone else have any other questions? All right, Edward, you can present the rest of it. Oh wait, I explained this. Okay, JK.
Yeah. So, what else is there to present? I guess we can just like go over like a simple model that. Wait, let me log in first, and then I'll just go over like a simple model that kind of works, and y'all could optimize it from there, and then just like kind of figure out how to like improve it. So I'll just share screen right now. You just submit the data. So like with this is like a starter code. There is going to be this part just automatically submits it for you. So if you just run this code, it'll do the whole thing for you essentially. Yeah. So kind of like the first thing. So like kind of how you want to approach this problem is that since you kind of see that there's like kind of curves and that kind of stuff, you probably should be using one of the nonlinear functions to model it. So the first instinct would just probably be instead of using a linear function, use something like ReLU or something like that. And since it's also like pretty curvy or something like that, you can just add like a couple extra layers where one of them is tan. There's going to be a lot of fine tuning involved, but this is like a general model that should work a little bit better than standard. And then you don't want a significant like drop, so just do something like that. And you can just train it. Yeah, and this should perform a little bit better than the actual one. This is like the diagram itself, kind of wonky. Yeah, see, this is the part that's going to be difficult. And yeah, so now I just achieved 47 MSE. So if we train it for longer, we can probably get improved results. So let's instead of training it for just 5 epochs, let's try something like 20 epochs. So since this is just like a really small function and all the linears are, and all the models are not like classifying stuff, it's going to be really easy to get really low MSE. So now I've gotten 25 MSE. And then we can just like make this further. Honestly, we should probably limit the number of epochs, I feel. I feel like not limiting the number of epochs. Yeah, we just want as low MSE as possible. I think we should be lowering. No, yeah, it kind of plateaus at 22. Yeah, okay, I remember now. So basically, this is gonna probably like plateau or something like that at 22, where it's gonna think that it's actually the optimal, but it's not actually the optimal. So now that it's actually after running this saves the outputs here inside test results. This is Windows, so it's gonna like look really kind of janky. So yeah, this is how the results look on my computer. And then you can just submit it here. Like this one. And yeah. Oh wait, 19. Okay, Stone, you get it. You got 12. Yeah, so that's basically how you submit your files. Yeah. It should generally run really fast because this is there's like a small function, there's not that many parameters. Add 0 to the end. And also the other thing is that at the end of the competition, we're actually going to run it on all 1,000 points instead of just 20. And as a result of that, your scores may change. Like as you can see here, I use the same code, but my score already changed. And that's because each time we're sampling on like a random 20%. So my score should be changing a little bit, or not.
Wait, you just no, it's not random set 20%. We just take the same 20%.
Wait, no, but that makes it.
No, but if he can do a random 20%, that means he can just randomly sample all the test data eventually.
Well, no, I feel like that's the same argument for if you use a definite 20%, no?
No, but if you only use a definite 20%, maybe let's say they get 0 MSE on that 20%, they'll probably fail on the entire set then.
No, but like the thing is, I feel like you can, now that you know that on this 20% you have 19, you can probably optimize based on this test set now.
You don't know what 20% is correct.
That is true.
It's the same 20% anyway.
Okay, you know what? I'm going to optimize my function.
Okay.
Instead of using Rayleigh, I'll use exponential.
Y'all can watch Edward tell you guys the answers, apparently.
I like exponential. Oh. No, I don't think I should be using exponential, actually. Exponential goes too fast. Yeah. Oh, 19. So exponential is like a pretty good function you should use also. And then honestly, you can just add more layers or change layers. And then hopefully you'll get a better result. But generally, I think the optimal one for this is going to be like a 2 to 3 layer function. Yeah. Is there anything else you want to add, Stone?
Is it a bug? I don't know how that data got 12.9. That should not be possible.
Oh my. Okay, so I need to optimize this. I think 2 layers of 10 might be best.
Well, nice to see that you guys have already started submitting. I see 2 submissions.
Let me try Sigma. I think Sigma would be pretty good.
Someone submitted 5 times already. Nice.
So honestly, it's like a pretty quick competition. It's more just for fun than anything else. And you can submit like a lot of times. You're both for the same submission. Oh wait, that might be me. Yeah, so honestly, a lot of this is going to be trial and error, where you try to figure out what functions work the best. So instead, let me try 100 epochs. So there's another thing that's really interesting is that some functions converge slower, but after converging, they're actually more optimal, which is also something you should probably look for, because like using sigmoid, it's still going down, even though after 100 epochs, even though it's after 100 epochs, whereas the previous one converged at around 40 epochs. So you have to like just make more epochs. That is the conclusion. But at like a certain point, there's going to be, it's going to like kind of like asymptote or something like that, which is kind of like it quote unquote assumes that it converges at a certain point. But it doesn't actually, because that's not like the most optimal. Like it learned some sort of function, but that may not be the most optimal. So yeah, I'm not getting that good of a result. You know what? I don't think exponential is actually the move, because exponential has like a really bad graph. And it
don't give away the answers.
Okay, never mind. Okay, yeah.
I don't know what the actual function is, but like I feel like the fact that Edward's saying exponential a lot or tanh a lot, it means it's tanh based.
Wait. Okay, I saw sharing screen. I don't think it's actually tanh based.
I don't even know what he did. Yeah, that's it for our workshop. I'm gonna go ahead and stop recording.